Okay, hello again, Borger High School. This is Howard's chemistry class. This is a continuation of the notes on Unit 2, Intro to Chemistry, and we'll be covering the TEKS, the things that the state of Texas says you need to know in chemistry. We'll be covering TEKS 2B through D, and you can read these while I've got the screen on, but we'll go over these also in class, so you don't have to memorize them right now. Look in your notes, and we're going to pick up right where we ended on the last PowerPoint video for your notes. Okay, so we're on Roman numeral number 3, the scientific method. Scientific method, that's something that you have talked about in every single science class you've had, and don't tell me otherwise. I know that it's there. Every single science teacher, science class that you've had, they go over the scientific method. When you're first learning how to do science, you learn a basic process or procedure to do that. It's kind of like when you're first learning how to drive. When you go in to take your driver's test, there are certain things that the driver has to do in order to pass that test. So you get in the car and you adjust the seat and you adjust the mirror. You put your seatbelt on. You check the outside mirrors. And it's been too long since I was in driver's ed class, so I don't remember all the things you have to do. But once you've been driving for quite a while, you can skip some of those things. You just kind of automatically do that. That's kind of like how it is with the scientific method. We here in chemistry class are going to be using and following the scientific method, all the steps of the scientific method. But when you go out to the professional scientists, they might start partway through the scientific method and realize, oh, this isn't working out at all, and then they can modify. They can regroup and start over. They don't have to follow it perfectly. We will, because we're beginners. We're not the professional researchers that they are. So the scientific method allows a systematic approach to solving problems. You can do the same basic steps over and over again, and when you follow these steps, you know that you have a good design set out and a reasonable plan for trying to solve that problem. Okay, start out. Capital letter A, the steps of the scientific method. State the question. What is your question or your problem? Don't get all philosophical about your questions here. You need to make it really very clear, very precise, not too wordy. Okay? The second step is the research. You're not going to spend a lot of time working out an answer to the question if somebody's already got the answer. You can go out online, or you can get these things called books, and you can possibly find the answer to your question without doing all the rest of the scientific method to get your answer. But if you've got a good question and you can't really, you know that there's not an answer out there yet, then you can go do some background research to see, okay, what information do I have that will help me come up with the answer? So when you do your research, you find out as much as possible about the problem. And a part of that research is, again, your observations. Those are things such as your sense of sight, taste, touch, hear, and smell. The third step is forming the hypothesis. And the old definition for it, the easy definition for it is an educated guess. And that's a nice, simple definition for an hypothesis, but it's a possible explanation for your problem. It's almost like you've done your research, now you're going to kind of guess, what do I think is going to happen? Typically, and the best of the hypotheses are going to be put into an if-then statement. If I do this, then this will happen, okay? Or as it says on the slide here, if this is done, then that will happen. So you have an if-then statement. It makes it really, really clear, and it makes it easy to find some of the parts that your standardized tests, like the TAKS tests and the EOCs, ask you to find. Like, what about the independent variable and the dependent variable? If you have your hypothesis set up as an if-then statement, then your independent variable will be the first part. If this is done, that's going to be the independent variable. This, whatever this is, that's your independent variable. That's what the scientist is doing. That's what the scientist is messing with. The dependent variable will be the second half of that. If this is done, then that will happen. Typically, the dependent variable is what we're measuring. So whatever we're going to go in and measure and see, hey, what's changing here, what's going on here, that's going to be the dependent variable. You'll hear that again a little bit later. Fourth step, so we had ask a question, do the research, form your hypothesis. The fourth step is test the hypothesis, and this is the part you guys like. This is the part where we run an experiment. In many cases in chemistry, you guys are being introduced to all of the chemical equipment, you're being introduced to some theories from the past. And so in many cases, we tend to skip over some of the first 3 steps and we jump right into the test the hypothesis, we do the experiment. And we'll do some of that, but we also want to use the full entire scientific method too. So we'll do a little bit of both types this school year. When you test the hypothesis, that's your experiment. And what you want to do is test the hypothesis. If I do this, then that will happen. So you have to do this, and then you have to measure that. So you're doing it in the lab where you have a really controlled environment. And my little thing here's going wonky here. I have no idea what the sound is going to be like. So you have an experimental position. You have the lab. You've got a nice, clean workspace. You've got everything, all the safety equipment there. You don't have to go out into the field and do the test. You can have a nice, neat lab to do this in. So you test the effect of one thing on another in a controlled environment. The 5th step, and for some reason it's really, really tough for some people to write everything down, and this is recording the data. You have to write down what happens. Now, a lot of times I'm going to give you a chart or a graph to fill in, but sometimes you're going to have to come up with your own. But no matter what, whether I give you a chart or a graph or you come up with your own, you also take into account the fact that you have to write some observations down, like what happened in that lab. So when you record the data, the scientist has to make careful observations and measurements, and then record it in a really clear manner. And I love science because we don't have to write out, especially when we're first learning, we don't have to write out 52 million paragraphs like you do in your language arts classes. We can put it in a chart or a graph, and then we can take a few sentences and explain that. It doesn't have to be 3 pages long. Charts and graphs, love, love, love those. Now, when I say write down your data and your observations, you fill in the chart or the graph, or you create the chart or graph, but then you also put over to the side what happened in the lab. Oh yeah, this one, it spilled on the table and it turned from a clear to a brown color when it did that. Or my lab partner spilled our chemical down the sink and we had to start all over. Or, all sorts of little things that happen. Oh, look, it started bubbling and fizzing. Those are observations. It may not be the measurement that was asked for in the graph or the chart, but it's something you noticed that took place, so you write it down. And when we talk about observations, there are 2 terms that always, always, always come up, and that is accuracy and precision. If you are accurate, it's like you're getting the right answer. You're getting the one that the book says is right. If you're precise, you may or may not get the right answer, but you get the same answer every single time. Gosh, you get the same. It's the same wrong answer maybe, but it's the same answer every time. So accuracy, if you look at the little arrows, accuracy would be the one where the arrows, the 3rd one over on the right, where the arrows are all hitting the bullseye. And then if you look at the one that's precise, I don't know why this is coming up. If you look at the one that's precise, it's where they're grouped closely together. My husband, when he goes out and sights in one of his new guns, he likes to know that they're grouped that a quarter or a $half could cover all the 3 holes that he does, and he knows that even if it's not smack dab on the bullseye, he knows that, oh, they're all grouped together, so it's just him that he needs to kind of modify a little bit. So if they're precise, they're close together, you're getting the same answer over and over again. If they're accurate, you're not only getting the right answer, and you can be accurate and precise, and you're hitting the bullseye every single time, or you can be precise, but not necessarily accurate. All right, again, your data should be in charts, graphs, tables, something easy to read. You can get a whole lot of information quickly out of a graph or a chart of some kind. It's much easier to do that than to read through someone's paragraph that they're writing out. Okay, so our first step was ask this question. Second step was do the research. Third step, form your hypothesis. 4, test your hypothesis. 5, record your data. And then our last step is form the conclusion. Your conclusion is basically where you say, yes, my hypothesis was correct or it was supported, or no, my hypothesis was just flat out wrong, it wasn't supported by the data. Now, when I say supported, I'm going back to look at your step number 5, your data. When you did that test and you wrote down what happened, did it agree with your hypothesis, or did it say, no, that hypothesis was way off? So this is where the question is answered, was the hypothesis supported or not supported, and where the analysis of the data is taking place. So when you analyze the data, you kind of look for patterns in the data, like, oh, there's some things that I see over here and some things I see over here. Or you look for trends and say, look, if I look at my graph, it continues to go up over time. I wonder if it will continue to go up, or I bet it's going to continue to go up for the next X number of minutes. All right? So you're looking at your data and you're using it to answer and check and see if your hypothesis was supported or not. And you're looking at the data to say, is that really good data? Is it, do you think it was somehow kind of messed up data? If anything happened in your lab that you know messed up the data, as long as you write it here in your conclusion and account for that, I won't count off on your lab. It's when I know that you messed up, I absolutely know you messed up, I saw it happen, or I know by the data it happened, and you don't say anything about it, that's when I'll count off for it. So let's say you're doing your lab, and your lab partner poured a chemical into the beaker and put some water in it when he wasn't supposed to. Well, you only had a limited amount of the solution, so you didn't get any more. And so you went ahead and did the experiment that way. That's going to mess things up. If you water it down, it's going to alter your data. As long as you tell me in your conclusion that, oh, hey, my lab partner did this, and I think this threw off our data. It's not, it's not what we expected it to be because he did this. As long as you write that in, you'll get full credit. If you don't write it in, then I'll count off for that. All right. The hypotheses that have been proven repeatedly over and over and over, and then over a wide variety of conditions, those can be incorporated into scientific theories. In many cases, you can think of a theory as being created of multiple hypotheses that a lot of people have gotten those hypotheses proven to be correct over and over and over again. So a theory is you can think of it in two ways. A theory is kind of bigger, maybe you can think of it that way, than a hypothesis because it's made of multiple hypotheses, and it's also more supported than a typical hypothesis. You've got a lot more, background to support you, a lot more experimental evidence to support you. All right. Now, we talked about this a little bit. We have some experiment parts. And these are things that you can guarantee, whether it's the tax test or the EOC, they're going to ask you about these. They're going to have questions that are asking you about these four things: the dependent variable, the independent variable, the constants, and the control. And sometimes the terminology that they use, it's not the easiest to remember what all these things are because it seems to overlap. So if you look at number 1, you must have a controlled environment. That means you have these variables, and a variable is just something that can change, like, the temperature can change, or the wind. You guys know the wind can change easily. Those are two things we don't have to worry about when we do the experiment in the lab because we have a controlled environment. It's going to be about 73 degrees in our classroom, and there's not going to be a lot of wind coming through there. So we control those variables there. By doing our experiments in the lab, we have a nice, neat, spiffy, controlled environment. Number 2 is the variables, and those are things that can change, right? Things that are changeable. Your hair color is a variable these days because we can change hair color. Your eye color even, you can put colored contacts in. We have lots of different things that can change, and those are all variables. Letter A, dependent variable. The dependent variable is the thing that you're measuring. It is the thing that changes because you're experimenting on it. Okay? Let's say you decide that if you nuke these rats, if you put them in the microwave and nuke them just for 10 seconds, then they will become super rats and be able to push a big wooden block across the floor. Okay? So your dependent variable is, can they move that, or how far can they move that big wooden block across the floor? That's the thing that we're measuring. That's the thing that changes because of our experiment. We nuked them, put them in the microwave for 10 seconds, and now they're stronger so they can push the block across the floor. Okay? So the dependent variable would be the strength. How much are they able to push that block across the floor? The independent variable would be, hey, we're nuking these little rats here. So independent variable, what are we doing to them? We are putting them in the microwave for 10 seconds. Dependent variable, what are we going to measure? We're going to measure how strong they are. How far can they push that wooden block across the floor? There's no way to just, I think, instinctively remember that. Those are things that you're going to have to sit down and study over and over and over again. And these won't go away. They'll be with us all throughout the school year. Now, I'm going to pick up my spiffy little pen and write on my bamboo and see if I can color on here. Can I? Oh, got to go back now. There we go. So I have no ink. Got to know how to do the ink. I'll be experimenting all throughout here, children. So just bear with me a couple of minutes. Oh, that one messed up. Yeah, let's continue recording. Let's go back down here because, you know, hallelujah, we only have a couple of slides left. Let us see. Is that what I want? No. There. Yay, there. I have no idea what this is going to look like when you guys get it. I won't do this again, I promise. Yes, here we go. Gotta find it again. Oh. One more time. Okay, I'm putting the pen down. Alright, constants. Constants are things that you have to make sure they stay the same. They stay constant all the way throughout your experiment so they don't screw things up. Okay? So we're talking about those rats, and we're going to nuke them for 10 seconds and then see if they get stronger afterwards and push the wooden block across the floor. Well, something you'd need to keep constant would be the size of the wooden block. You want them all pushing the same size of wooden block. How long you nuke them in the microwave. It's got to be 10 seconds each time. You want to be consistent. What kind of food and how much food are you feeding the rats? You want to keep it consistent. So it's not like, oh, well, if we starved those other rats, that's why they weren't strong. You know, you have to keep things constant so they don't mess up your experiment. And then finally, letter D, the control. The control you can think of as normal. When it says on the page it's the standard that you compare your results to, it's the norm or the normal. You have to know what normal is before you can know if your experiment actually made it do something different, right? So the control is normal. You have to know, you have to be able to compare it to something normal. So in our rat experiment, we would have some rats that we nuked, and then we would have some other rats that we didn't do anything to, but they were in the same environment, they had the same kind of food, the same amount of food, and we're going to make them push that wooden block across the floor just like the other rats, right? So we have normal rats that haven't been nuked, and we compare them to our scientifically manipulated rats where we nuked them in the microwave for 10 seconds. No rats have been harmed in the making of this podcast. Okay, a fact, a little bit more vocab. A fact is a statement that's agreed upon and undisputed. However, it can be changed. Facts are not written in stone. If you'd gone back into the 1100s, it would have been a fact, you would have learned it in school, that the earth was flat. Oh, yes, the earth is flat. Well, we get more and more and more data, and we find out that, oh, sure enough, the earth is not flat, and I don't know, I'll take care of it later. And we know that the earth is round, so the facts today would be that the earth is round. A hypothesis is a possible explanation for something, and a hypothesis can be altered, obviously. We can decide whether or not the hypothesis is supported by the data or not supported. And again, if we have a multitude of hypotheses and they prove true over and over and over again in a variety of circumstances, then we can take that hypothesis and say, this is a good piece, let's put it into a theory that we have over here that's kind of covering a broader topic. All right, so we've talked about the steps of the scientific method, and you filled in the second part of the notes, and we will continue the discussion in class.